Okay, so this video has a look at catalysts, what they are and how they work. So this is video number 5 in the series of 7 short videos about rates of reaction. So I'm going to cover with you what a catalyst is, how a catalyst works, and then we'll have a look at an energy profile. So a catalyst is a substance that speeds up the rate of a chemical reaction, but is chemically unchanged at the end of the reaction. Now, really importantly, a catalyst can't make a reaction occur that wouldn't occur in its absence. A catalyst will simply speed the rate of a reaction up. Now, because a catalyst is chemically unchanged at the end of a reaction, that means a catalyst can be reused. Now, let's imagine we've got a reaction that occurs in solution, but we've got a solid catalyst. So because the catalyst is chemically unchanged, that means we should have the same mass of a catalyst at the end of the reaction as we had at the start of a reaction. Now, how does a catalyst work? Well, it makes a reaction occur in a different way. So we would say a catalyst works by providing an alternative pathway with lower activation energy. So a catalyst does not increase the energy of the particles. What a catalyst does is it makes the particles react in a different way, and that different reaction pathway has got lower activation energy. So if we have a look at this in terms of a diagram, so if the black bar is a piece of solid catalyst and we've got two particles that are going to react together, in this case two elements. So what a catalyst can do is it can attract reactants onto its surface, and it then holds them close to one another, and it holds them in a favourable orientation, and that means that the activation energy for the actual reaction is lower. So in this case, the reactions happen. We've formed a bond between the two elements that we had, forming a compound, and the last thing that happens is that the product is released from the surface of the catalyst. Now let's have a look at an example. Now hydrogen peroxide decomposes to give water and oxygen gas. Let me do a chemical equation for that. Now if you pour a solution of hydrogen peroxide into a conical flask, it starts to fizz after a while because of the bubbles of oxygen gas that's being produced. But the rate of reaction is extremely low, so you see very few bubbles and a low rate of fizzing or effervescence. If, however, you add a catalyst, now one catalyst for this reaction is manganese dioxide, and that's got the formula MnO2. It's a black powder, and if you put that into the conical flask, what happens is the rate of reaction increases massively. And we get absolutely loads and loads of bubbles of oxygen gas within our conical flask. Now, in a chemical equation, we show a catalyst by writing it on top of the arrow. So here I would put MnO2 there. Now remember, a catalyst is chemically unchanged. So for example, if we added 1 gram of manganese oxide, this black powder, and then at the end of the reaction, we filtered out the manganese oxide and dried it, we would still have 1 gram because it's chemically unchanged by the reaction. Now remember, the reaction was already occurring. A catalyst cannot make a reaction occur that wouldn't occur in its absence, but it can increase the rate of reaction, sometimes thousands and thousands of times. Now there are quite a few different catalysts that catalyse this reaction. And what you could do is you could connect this conical flask to a gas syringe, and you could have the same volume of hydrogen peroxide every time, add the same mass of catalyst each time, and you could time how long it takes to collect a certain volume of oxygen gas. Now the best catalyst will produce that certain volume of oxygen gas in the lowest time. It will have increased the rate of reaction the most. Now let's have a look at reaction profiles. Now please check that this is on your specification. Now a reaction profile shows the difference in energy between reactants and products. Now this would be an exothermic reaction because the products are at lower energy than the reactants. That means that energy has been given out to the surroundings during the reaction. Now, if I join the lines together, we would get something like this. So let me show you what the different parts of the graph are and what they mean. Now the difference in energy between the level of the reactants and the top of the curve is the activation energy. And remember, we can give the activation energy the symbol EA, so capital E and a subscript A. And the difference in energy between the reactants and the products is the delta H, the enthalpy change, or the molar enthalpy change, which is of course linked to the heat energy given out during the reaction. Now, what does a catalyst do? It provides us with an alternative reaction pathway or reaction route of lower activation energy. So it will not change the energy of the reactants and the products. Quite simply, a catalysed reaction might look like this. So all that's happened is the activation energy is lower. So a catalyst has not changed the energy of the reactant particles, it just provides them with an alternative reaction route or reaction pathway of lower activation energy. So therefore, more of the particles have energy greater than or equal to the activation energy, which is lower. Okay, so that's rates of reaction catalysts, hopefully made simple. Thanks for watching.